Okay, so today, just one equation, only one board. I won't erase anything. Just one board. And so what we're doing today is the signal equation. And so this kind of relies on this whole concept of the phase-sensitive detection, which we haven't talked about yet. That's on Monday. It doesn't hurt to sort of go over, and it's kind of almost the same thing as the phase-sensitive detection, but we're going to sort of get down to what's the bottom line for the signal that comes out of your brain that is used to reconstruct the MRI. So this is actually going from the oscillating protons to the voltages that actually appear in the coil that you record, and what's the nature of that. And so I always, every year I always say, this is sometimes called the popular signal equation. It's kind of like where there's some unpopular signal equations. It just always kills me, like when mathematicians are sort of trying to be a little colloquial. So this is the popular signal equation. So we'll go over, basically, and the way we mess with equations is, you write up an equation, sort of a useful general equation, but it's, in some respects, it's kind of useless because it's got too much detail in it. And then we do various hacks and sort of like, let's ignore this part and we'll replace this part with this thing that's simpler, and then we get down to our final thing. So that's the goal. So we start off with a sort of a more complicated equation, and then we'll throw most of the parts of it out and make a bunch of assumptions to get to our signal, our final signal equation. So our signal equation, what does it start off with? It starts off with a new symbol. Like the very first thing is like another, what's that? So that's a capital phi or phi. So, like a small phi looks like this, or sometimes people, will write it like something like that. That's a small one. This is a capital one, capital Greek phi. And this is something that's sort of changing over time, function of time. Could be a function of space too, but we're just worried about the time part. And so what is that? So that thing is called the magnetic flux. And so, like the flux capacitor. So what does flux mean? That just means flow. But it's actually not a flow. So how did people sort of think of magnetic fields? If you've seen sort of drawings of magnetic fields, you'll see they often are drawn like lines. So you have that's not a good magnetic field. Let's make another better magnetic field. So they often draw magnetic fields as lines, and initially people thought that there was something kind of flowing across these lines, and that's why it's called flux. But it's actually not. It doesn't have anything to do with flowing. It refers instead to just the amount of magnetic field. And so it's a scalar. So it's just it's not a vector. It's a scalar. It's just kind of an amount. And what is that amount? That amount is if we have some coil here like this, and it's got a twisted pair here, so that it'll just sort of pick up magnetic field from that part. If we sort of imagine the plane of the coil, what is the flux? And so there's going to be magnetic field vectors at each point, coming through this coil, and they're pointing in different directions. They're vectors actually pointing in different directions. And so what is the flux? The flux is if we take that magnetic field vector and find the projection onto the plane of the coil, and then just sum up the length of all those vectors that are perpendicular to the coil and get a number. So it's more like how much magnetic field is there, passing through the plane of that coil. So that's what the flux. That's one of the ways you can think of what the flux is. But we're going to think of it like in the case of like a coil with a brain in it. And so, what is our general equation for the magnetic flux, which we have to do? This is not the final answer. We're going to take the derivative of this to get the voltage, but we'll start off with the flux first, just the amount of magnetic field. And so our first, it's a kind of totally useless equation, is let's sum across an entire object of two things that are dot producted with each other, and they involve a B, and an M. So here's a B vector, and that vector is different at each point in space, and so that's a B vector. And so what does that R mean? That R vector is just a way of writing x, y, z. So we could put B as a function of x, y, z, or we could put B as a function of R vector. So it means the same thing. So we just went to each point in space, and then there's a vector at that point in space, the B vector. And what is that? So that's the magnetic field either detected or generated. So it's kind of sort of goes both ways. So if we put some current in the coil, so detected or generated for each point in space, by a coil. So it works both ways. We can either put some current in the coil and then get a field, or we can get a field and then look at what current is induced in the coil. So that thing is then dot producted. So that's our original dot product. So this is dot. It's not a multiplication. I mean, it's a vector multiplication dot prod with another thing, and the other thing is the local magnetization, which we've already beat to death. So here's the local magnetization vector. That's caused by like how the protons are arranged in a particular voxel, and that guy is also different at each point in space. So there's another R vector, and then we're integrating, which just means summing, summing across all of space. So this is object all R's. So what is that? So what is this guy? This is local mag of object. So this just says, and what is a dot product? Dot product is like the cosine. So when the cosine of the angle between two vectors is small, when the angle between two vectors is small, the cosine is large. That's when the cosine is the largest. So two vectors that are very similar in direction have a large number. And so this thing says like the magnetic flux is equal to go to each point in space and find out what is the magnetic field direction that the coil would generate at that point in space, and see how similar it is to the magnetic field of the actual stuff in the voxel, and then sum that up across all of space, and that tells you how much flux this coil will see. So this this thing is like a voxel. That's like for every voxel. So this equation says like, the magnetic flux equals for every voxel, see how similar the magnetic field generated by the coil is to whatever magnetic field is in the sample. So that's a simple, relatively simple to understand equation. So then we should, which order should I do it in? So we'll do, oh sorry, I left out one thing. This guy is changing over time because we have a time over here. So this guy is changing over time. Sorry about that, guys. Yeah. So time is just a single number, not a vector. So at every point in time, this magnetic field might be different. This guy is not changing in time because the coil is just sitting there. If you're not moving the coil, it's just sitting there. Okay, so now we'll put up the second equation, which is the one that we need in order to figure out what our signal in the coil is. So this just tells the magnetic flux in the coil, but you can't directly measure that. And so here's our second main equation. So the voltage over time. So the voltage over time is equal to the negative of the partial derivative of the flux. Okay, so now we introduce one more thing, the partial derivative. So we'll say what that is. So here's that flux now. It went over here. There, and what does the partial derivative means? So this thing means the flux might be different in different places, but we don't care about that. Just change due to t. So just change due to time. That's what the partial derivative means. So there might be changes in flux in different parts of the coil, but we don't care about that. It's just the change over time. So it's the negative of the partial derivative of the flux with respect to time. And that will tell us what signal we actually see in the coil. So now it's getting slightly worse, but we'll throw out most of the stuff. So now we have to find the partial derivative with respect to time. So just look for changes in the flux, and then we just substitute in this equation here. So then we got this equation, sum across the entire object of this B vector, which is different at each point in space, and dot producted with whatever the local magnetization is at each point in space, and that one's changing in time, summed across the whole all of space. Okay, so now what we do is we want to make our life simpler, and in various ways. And so we'll have a whole series of simplifications on this side. So the first one is ignore Z. And I already mentioned this before. Why do we ignore Z? So the Z magnetization in our local magnetization is changing. That's like T1 regrowth. It starts off, if you do a 90-degree RF pulse, you end up with 0 Z magnetization, and then it will slowly grow back up. It takes a couple seconds. But it's so slow that when you work through the equations, it doesn't generate a substantial signal in the RF coil. Now it does generate a tiny, tiny little signal, but it's so tiny that you can sort of ignore it. And if you look at radio waves, like say the radio waves that are coming out of your cell phone, how do we think of those classically? We think of them as, at each point in space, there's a magnetic field and an electric field, and those, as you sort of like go across space and time, those things are changing. So the magnetic and the electric field are sort of like, they're at right angles to each other, and then they're changing, and then they're becoming, negative, still at right angles to each other, and then they go back to zero and then become positive again. Those kind of disturbances can propagate through empty space. But those kind of disturbances don't happen much at low frequencies. They mainly happen at higher frequencies. Now, they still happen at lower frequencies, and if, like the military has tried to communicate with submarines using very low frequency radio waves, but it's so inefficient, you have to essentially hook up an entire power grid to the antenna to generate a signal that's big enough that will actually penetrate through the water. So basically, we can ignore the Z component of the M field and effectively the B field also. So that's the first thing. So get rid of that. So just XY. So that simplifies our equation first. Okay, so now this thing. So like what, that could be anything. So this is kind of a useless equation because it just says there's some function, we don't know what it is, and it just tells us like what the magnetic field is at each point in the brain. But it doesn't tell us anything about it. It's just like, so how could we integrate it? We don't know what it is. It's just like, it's just, God said it's whatever the magnetic field is at each point in the brain, but it's completely unknown. So it's kind of a useless, it's kind of a useless thing. And so what we're going to do is we'll replace that with something that's kind of more reasonable to make our life simpler to solve the equation. And so basically substitute a simple brain. So what is, what are we going to stick in there? We'll stick in the following. So this is the magnetization, now just in the XY direction as a function of time. And we're just going to insert something in there, and that thing is, whatever the magnetization was that we started off with. That's our initial condition from our block equation solution. And then we'll start off putting a decay in, so there's some T2 decay occurring. And remember, at time t equals 0, this e to the minus 0 is 1. And so if you're multiplying by 1, that's just a regular multiplication, then you're not doing anything. And then as time goes on, it starts rolling off, going down. When you see that, you think that in your head, starting at 1. But then we're going to assume that we've got a signal that's rapidly rotating around in the XY plane. So then we have that guy. And what do you think when you see this guy? You think, oh, that's a vector of amplitude 1. It's a vector of amplitude 1 pointing in that angle direction. So that's the meaning of that one. So this guy, so it's important. So this guy's complex. So it's got two numbers. It's got a real and imaginary. This guy's real. This guy is real. And this one's complex again. And when you multiply a real times a complex, that just scales the complex vector. It doesn't rotate it. Okay, so now the next plan is let's just ignore the decay. So what does that mean? So that means, t equals 0. So if we ignore the decay and substitute in t equals 0, then that turns that guy into a 1. So that guy, goes to 1, and so then that gets rid of that guy. Okay, good so far. But now we've got to take the derivative of this thing. So how do we take the derivative of this thing? So remember we were taking derivatives of this e to the minus t, and the way we took the derivative of that is we said, how do we take the rate of change, the derivative of it? We just take the derivative of the exponent and multiply it by the whole thing. And so what's the derivative of this guy? So there's several ways we could do it. We could just do it. We know that thing is equivalent to a sine and a cosine, so we could take the derivative of a sine and a cosine. Let's just write that out. So what's the derivative of a cosine? So here's a cosine. What's the derivative of that? Well, derivative is the slope, and so this guy is that guy is cos. So the slope is 0 there. So the slope is 0. The slope is biggest over here. And then the slope is 0 here again. And then the slope is biggest over here, but in a negative direction. And so, and then it's 0 again. So what is that? Well, it turns out, sorry, I drew it the wrong way. It's just a negative sign. So the slope is 0 here, and then it starts going negative, and then it's biggest, right there, and then right there it's 0, and then it starts going positive here. Sorry, I said it wrong, and then it goes back. And so what is that? So that guy is just negative sign. So that's kind of convenient. You could do it. You could split this up into sines and cosines and take the derivatives that way, but you could also just do it directly. And that's, like I said, the reason people, mathematicians, physicists use that is because you can just operate on it directly as if it was just an e to the minus t. And so how do you operate it? Well, you have to take the derivative of the exponent and multiply it by the whole thing. And so what is the derivative of, e to the, I don't have quite enough space here. Let's put it underneath. So what's the derivative of, e to the I omega t? It's just going to equal the derivative of the exponent, which is I omega times the whole thing, e to the I omega t. So when I first saw that, I said, oh man, now the I has escaped. We had the I safely in the exponent where we know it just turns this into a complex, amplitude 1, amplitude equals 1 number, and whose direction is indicated by what that angle is. That was all okay, but now what does it mean to have an I out of there? It escaped. So just think about it as the way we do complex multiplication. So I is a complex number. It just happens to have a real part equal to 0. And so what is I? It's a number like this that just points up. It's got a length of 1, and it's pointing up in that direction. And so when we multiply by an I, all we do is we just rotate 90 degrees. So when you see just a bare I sitting out there, it just means rotate this complex number by 90 degrees. So that sort of seems okay. It's kind of related to sines and cosines because we kind of, the derivative was basically of a cosine with a minus sign, and that just kind of was like a 90-degree rotation of the angle. So it all sort of fits together in some twisted way. But then you got omega in there. Why is omega outside? Well, the actual signal is 100 and, here's 1 second. The actual signal is 123 million cycles a second. And so the derivative of that is going to be very steep. because, it's almost a vertical line. So the slope, so that's why we've got like such a big number there. How could the derivative of this thing suddenly be huge? But it should be huge. Okay, so that's the derivative that we've got to take, because we've got to do the derivative over here. But now let's assume phase-sensitive detection. And so phase-sensitive detection basically gives us the frequency difference. So how do we assume phase-sensitive detection? We assume that we're not detecting the actual frequency. We're just detecting the change in frequency, the offset, the frequency offset from the center frequency, kind of like a chemist would. And so then, instead of this, we end up with, I, change in frequency, which is going to be a smaller number, times, e to the I change in frequency time. And so then let's just throw out the I. We don't really care about the I. It's a constant, and so these guys are going to be a constant for our derivative. So we can just throw those guys out. See, this is what I'm saying. Like you got to make your life simpler by inventing things and then throwing even some of the things that you invented out of there. And so now we can also throw out this guy, because this guy's a constant. We're taking the derivative of a constant, so basically, this guy's constant, so we can kind of ignore this guy, or just include this constant plus this constant all into one number at the front. And so then, and then we're just doing this for time, t equals 0, so we don't have to worry about any decay in there. So what's the final answer? So the final answer is that this signal that we're getting, so let me just write this out one more time. So the signal that we're getting, which is a complex signal over time because of our phase-sensitive detection. So when we assume phase-sensitive detection, one other thing we've done more than just change to the frequency offset, the frequency difference for each local bit. How different is it from 123 megahertz? But we've also, made real to complex. So we've turned our signal from a real signal of voltages coming out of the coil, and we run it through the phase-sensitive detection, and we get two numbers. So here's those two numbers that we're getting out of the coil, and what's the equation for that? The equation is basically equal to, the derivative, the partial derivative with respect to time of this thing. Now times what we substituted in there. And so what we substituted in for this guy was the MXY for a particular point in the brain, and we're ignoring decay, so we'll just say just at the 0 point in time. This guy should be down here, sorry. So, no decay. And then times this, e to the minus I change in frequency at a particular point in space times time. So so these differences in frequency are actually spatially dependent. Spatially dependent. So this means, like, for each voxel. And then finally, we can just, finally write out our popular signal equation, and then just try to get some idea of what it actually means. So here's our popular signal equation. So it's a vector, complex value, xy vector, which, after we've taken the derivative, is, and when we took the derivative, we sort of ended up with the same thing, right? So, here was the thing we started, and this is before we took the derivative, and we're going to take the derivative of this guy, but, what did we end up with? Well, basically the same thing. That was another case, remember, of just like the e to the x business. So when we take the derivative of e to the x, it's a special function that just happens to be the case that the slope at a point is equal to the value at that point. So this guy is, e to the x, the derivative of e to the x, and the derivative of the slope of this function happens to just equal the value of the function there. And so that's a handy kind of thing, because then whenever we take derivatives, we end up with the same thing. So you might wonder, like, I got rid of the derivative, but how come we ended up with the same thing? That's what we were doing over here. Okay, so what do we end up with? We end up with the xy magnetization amount. That's this guy right here, at a point in the brain. And then that's multiplied by these oscillations that we just assumed were coming out of the brain. So that was our assumption for what this unknown function is, this unknown sort of local magnetization function is. And so here's the minus I. It can be minus or plus. Don't worry about that. So here's that offset from the center frequency, which the phase-sensitive detection did for us at a particular point in the brain, at a particular voxel in the brain, times time, summed across all voxels. Okay, so that's our final popular signal equation. So now let's just sort of see, and this is, across the object, summing across the object. And so let's just look at this. So this signal is a complex signal, so it's got a real and imaginary part. This guy is a scalar. It's just the amount. This thing right here, this sum, is just done by the coil. So this is sum by coil. It's summing across. It's summing across the whole object. And this thing is a complex amplitude 1 rapidly rotating thing. Complex amplitude equals 1 rapid rotating. And it could be rotating at different frequencies in different parts of the brain. So it just depends on, what part of the brain. But for a single part of the brain, it's rotating at one frequency, amplitude 1. And then this just tells how strong it is at that part of the brain. So what does this actually mean? What does it actually mean? So let's just think about the brain. So here's let's put a brain here. So here's Homer Simpson brain. So somebody's in there. They're being scanned. So we ignore the xy component. So we're only looking at these. We ignore the z components. So we're only looking at the xy components. So here's the little planes that I'm trying to draw. And at each plane, so those are all the voxels. This is a voxel. One is 1r, 1 xyz. So that's a voxel right there. And so we just get a very concrete picture of what this equation says. So this equation says at each point in time, what the signal is going to be whatever direction this thing is pointing. And what direction is that going to be? Well, it's going to be, this is the angle, right? That guy's an angle. So it's going to be whatever time we're currently at, 1.3 seconds. It's that 1.3 seconds is going to be multiplied by, how much of an offset we have, and to get an angle. And then this thing will give you a vector that is amplitude 1 pointing in some angular direction. And over time, the angle will change, and it will keep wrapping around, millions of times. And then we have to multiply that amplitude 1 vector by however much magnetization is there in the xy plane. And so that's what's going to be present here. There'll be some magnetization vector along that circle for 1 dr. So for 1 voxel. This is, for every voxel. For every voxel. But that's that one, and this guy, is going to be pointing in some other direction, and this guy, say, maybe pointing in that direction. This one's here. They're all over the hell. All different directions. It can be any old direction at any one point in the brain. Okay, so now what is this sum do? So let me just specify it more. So this sum is actually a complex sum. And what does that mean? That just means like tip to tail. So concretely, what does it mean? It means like just take the local xy magnetization vectors at each point in the brain and add them up. That's it. So, what is the point? Well, they literally just take these, if we could somehow just look at them in a plane. So if we just looked at them like from this direction, let's look at them from, here's the eye. Look at it from that direction, what does it look like? Well, there's going to be, a magnetization vector, a small one like that, and then maybe you've got a big one like that, and then maybe you've got a slightly negative pointing one, and you got a big one like that, and you just add all those suckers up. And then you get one data point. So that's where you started. So here's one data point. This is 1 ST. So it's one complex data point. So that's fundamental. And this is being picked up by the coil. So I didn't draw a coil. We'll put a coil in there. So here's the coil. Coil over here like that. But it's really important to keep in mind, so it's the entire head. Every single data point comes from the entire head. And what is a data point? fundamentally, it's just find the XY component of the magnetization at each voxel and then just add it up. Simple as that. So this thing, this part of the equation is just a length 1, and so it's scaled by, so this tells you how long that arrow is at each point. This part tells you how long it is. This one just tells you the angle of it, because the amplitude of this guy is 1, of this vector is 1. But then what does the coil do? It literally, now you could say, well, maybe it picks up a little more strongly from the eye. Yes, that's true. But the important point is it's picking up from the entire head. And what is it picking up? It's not just picking up any old signal. It's picking up a vector sum. So that's why it's the popular signal equation, because it really describes what the signal is. So the signal, any single data point, so this guy, this is one data point, one MRI data point. And all MRI data points are like this. And so what is that? It's just the vector sum, just in words again, vector sum across entire head of local XY mag vectors in each voxel. So that's the bottom line. It's the local vector sum of the local XY magnetization summed across the entire head. And all MRI data points are like this. So now at this point you're probably thinking that's kind of looking bleak. Like how do you get a voxel out of that? So every single data point, every individual data point comes from the entire head. And out of that, we're going to make these tiny, tiny little voxels, like, 1 millimeter voxel like that. We're going to find out, actually, that's what that millimeter voxel is, and the one right next to it's got a different signal in it. So how on earth do we do that, given that every single data point comes from the entire head? But this is the popular signal equation, and we actually do use this through a Fourier transform to generate distinguishable signals from pieces of the brain that are 1 millimeter from each other. But the important point is that all the data points come from the entire head. That's one important point. So vector sum. So all data points come from the entire head, but the other critical thing is that it's a vector sum. And you can't really understand this without getting the concept of it's a vector sum of these local XY magnetizations across the entire head. And because it comes from these simple considerations that the magnetic field in the coil is the flux through the coil is basically just sort of how similar, the sum across the entire head of how similar this local magnetization signal is to the coil magnetization direction. And then in order to calculate what the signal is that comes out of here, the actual voltage, this is the voltage that comes out of the coil. What is the actual sort of that's volts going in that direction, time going in that direction. What is the signal that comes out of the coil? Well, it's just the derivative, the partial derivative. How does the flux change across time? And then we just have to take the derivative of this thing. And then how do we do that? Well, we made a whole bunch of assumptions to simplify it. And we just assumed we had some kind of oscillating signal. And then we threw away the decay, And then we said, oh yes, and by the way, we're doing the phase-sensitive detection, so we're just getting the offset of the signal from the center frequency. We're not getting the actual rotating frequency. And then we take the derivative of that, and the derivative turns out to look just like that, just like the original, after we threw away sort of some constants at the beginning. And so then we got to here. And so this is what our signal is, the sum across the entire head, vector sum across the entire head of the XY magnetization at each point in the brain. And somehow out of that stream of numbers, each of which came from the entire head, we're going to construct some voxels. So that's the plan for next week. So I finished a little bit before, so now we can have some time for some questions. So any questions about the popular signal equation? Yeah.
In your equation, you gave the voltage. You have this opposite of the partial T, which is like T, and then the negative is not there at that. Did it get absorbed into the bar, or why is it not there?
Yeah, you could put that in there. Yeah. Yeah, a lot of times people just kind of ignore it because it's kind of a constant, but yeah, you could put it in there. Yeah. Yeah, sorry about that. You could put it in here too. But it won't change the main point, which is just this vector sum of the local magnetization across the head. You can see the reason why the MRI physicists don't want to tell you this part, but literally, if you don't have this part in mind, that you're summing up all these, differently pointing vectors, all is lost. You can't understand it. And the problem is it's tied up with the phase-sensitive detection. How do we get this kind of like complex number out of just one set of numbers in the, that's coming out of the coil? And so that's what we'll talk about on Monday. Where does that extra information come from? But without that extra information, all is lost. But this was what the chemists were doing this already way back, in the 1950s. So this wasn't a new phase-sensitive detection wasn't a new invention. Just for MRI, they were already doing it. So any other questions about any part? We can go back to the beginning, doesn't matter. The most basic part. Yeah. So the question is, why do we ignore the Z component? So the reason we ignore the Z, I didn't write it up here. So the reason we ignore the Z component is it changes so slowly. That's why we ignore it. Changes so slowly. And the result is no sort of change in the flux due to this guy. Or the change in the flux is so tiny that you can just throw it out. So that's the reason we ignore the Z component. It's just changing too slowly to generate any, because this voltage is all about the rate of change of the flux. And so the rate of change of the flux due to the Z component is too slow to make anything. So we just essentially ignore it. Now, you might think, well, what about T1? T1, how do you get a T1 weighted scan that measures the Z component? Good question. You can't measure it directly. You can't measure the Z component directly. So you go into the magnet. It takes you a couple seconds to get magnetized in the Z direction. You can measure that in a scan, like a structural T1 weighted scan. But you're measuring it by just measuring. This is the only signal. This is the only signal that's available. So you're measuring. We'll see how that you can make a pulse sequence to measure the Z component, even though our raw data is strictly the XY component. Yeah, but that's the reason we ignore it. It's just it changes. The Z component of the magnetization changes so slowly that it doesn't make a substantial change that makes any voltage that we can measure. It's millions of times too small for us to see. It's there, it's just too small. Whereas the change in the flux due to the rapidly rotating XY thing, that's going 123 million times faster than the Z component. So it's off by, you know, a tenth of a billion. Okay, popular signal. Yeah, so this one is stars on this one because this is worth remembering. It's easy. So the popular signal equation. Okay. So we're still like pretty far from images, like, you know, how the heck do we get an image? We really have to sort of go over the Fourier transform to see how it works and sort of fiddle with it. And then we'll hopefully get a concrete idea of how you can get this fine-grained image out of this kind of a signal. So we started, it's a low point. We're starting at a low point. Everything looks kind of hopeless now, but it'll get better. Okay, any last questions? I actually finished on time for once. Okay, well, see you guys on